Hello, my name is Jeffrey, and this is my video lab report for Physics 2211M Lab number 2. To introduce this lab, let's first analyze its purpose, its models and fundamental principles, and the main result. The purpose of the lab is to apply Newton's second law, aka the momentum principle, to observe the properties of a falling object in real life and in computational modeling with and without drag, and to graphically analyze its position versus time and velocity versus time of a falling object with and without drag. Because this lab is all about a moving object, it's important to apply Newton's second law of motion. To predict the object's motion, we need to know the net force acting upon it, its velocity, and its position at regular intervals, or time steps. Newton's second law reveals the object's net force, as it states that F net equals ma equals m delta v over delta t equals delta p over delta t. Free body diagrams, such as the example shown to the right, can be used to illustrate the net force. Once we know F net, we can plug it into the velocity update formula, v final equals v initial plus F net over m times delta t. And in general, once v initial and v final are known, both values can then be used in the position update formula. R final equals R initial plus V average times delta t. As for the main results, the observational data and the computational model without drag were drastically different. However, the observational data and the computational model with drag were fairly similar, but deviated slightly due to potential sources of error. For my observational data, I used a whiteboard eraser as a system, with the Earth and the atmosphere as its surroundings. The reason why the atmosphere is included in the surroundings is because air particles are what cause drag, which is a force that must be considered in real life. The initial conditions of the eraser is at rest and at the origin at t equals 0 seconds, and it is assumed that it falls along the negative y-axis. For the sake of simplifying the position update calculations, it's also assumed that the average velocity is equal to the final velocity at each time step, since net force is non-constant. Once I recorded my video, I uploaded the video to Tracker, with the reference measurement being the drop height of 118 centimeters or 1.18 meters. I also made the x-axis parallel with the bottom of the eraser, and the y-axis roughly in the middle of the eraser. I then assigned the eraser as a point mass, and manually selected its lowest point along the y-axis at each time step to gather position data, as shown to the right. For my computational model, I modified the GlowScript template to correlate with my observational data. I edited the initial ball velocity vector and the delta t variable. For the model with drag, I assigned a b value determined through trial and error. However, for the model without drag, b was simply set to 0. Within the calculation loop, I calculated the weight force and drag force in separate lines, and then summed them together to determine the net force at each time step. This net force value was then plugged into the velocity and position update formulas. I also changed the print statement to print data that I could paste into a spreadsheet. This is what the output of the program looks like for the model without drag. Note that the slope of the position versus time graph is negative and concave down, while the velocity versus time graph has a negative linear slope, indicating that the object's velocity does not change without drag. This is what the output of the program looks like for the model with drag. While the slope of the position versus time graph is negative and concave down, the velocity versus time graph is slightly concave up, demonstrating how the object's acceleration decreases in magnitude over time. Here's the data from both Tracker and the two models pasted into the same spreadsheet. As you can see in the graph, the model without drag deviates significantly from the observed position versus time, while the model with drag has a much closer correlation. However, even the model with drag deviates slightly from the observed data. This deviation can be attributed to several sources of error, including camera lens distortion, motion blur from the eraser making its edges unclear, human error from manually placing all the tracking points, and the eraser slightly tilting as it fell, as this would cause the surface area to change, would mean the v value would be non-constant. For the computational model, this would also be rounding values derived from the tracking. Now to recap, the computational model without drag displays velocity increasing in magnitude at a constant rate, while the computational model with drag displays velocity decreasing in magnitude over time, suggesting a terminal velocity. And at terminal velocity, drag force and the gravitational force would cancel each other out, making F net in the y direction equal to 0. Now, if the object was initially thrown downward, terminal velocity would be the same, but the object would theoretically reach terminal velocity in less time. This is proven through a modified version of the simulations, where the while loop continues until change in velocity is insignificant. With 0 initial velocity, it takes about 1.848 seconds to reach terminal velocity, while it takes 1.188 seconds with an initial velocity of 5 meters per second downward. Note that the horizontal asymptote indicating terminal velocity is roughly negative 6.6 meters per second for both graphs.